Okay, in this video I'm going to be showing you solutions to some of the homework problems from coordinate geometry, midpoint, and distance. I will be showing you problem number 1, 5, 6, 8 through 10, 12 through 16, 20, 21, and 23. Alright, let's start with problem number 1. A segment has one endpoint of -2, 4 and a midpoint of 3, 5. Find the coordinates of the other endpoint. So let's make a little sketch here. One endpoint of the segment is -2, 4. We're missing the other endpoint of the segment, but I know the midpoint of the segment is 3, 5. So if you think about your midpoint formulas, I know that I should be able to take the two x coordinates and average them to get this x value, and I should be able to take the two y values and average them to get the y value of the midpoint. So I know that -2 plus this x value of the endpoint divided by 2 should come out to be this 3, and I know that the y value plus this y value divided by 2 should equal the y value of the midpoint, which is 5. Now I just need to solve. I'm going to multiply both sides by 2. That gets this to be 6. If I add 2 to both sides, that's 8. Here, if I multiply both sides by 2, I get 10 on the right, and if I subtract 4, I get 6. So the coordinates of that other endpoint would be 8, 6, just using the midpoint formula. All right, let's move down to number 5. It says find the area of the parallelogram with the following vertices. So I'm going to make a little sketch here. I'm at -1, -1 for A. For B, I'm at -2, 3. C is at 2, 3. And D is at 3, -1. So you can see we have horizontal base here, which matches the horizontal top segment. And then we'll connect those pieces. So if you remember from our previous chapter, area of a parallelogram is base times the height. So when I look at my diagram, I see a very nice horizontal base. Right? It's a horizontal segment. Horizontal segment means I'm going to look at the x coordinates, right? And if you remember this from our previous problems, to find the length of a horizontal segment, I take right minus left. That comes out to be 4. Now the height is the problem because I'm not really even seeing the height when I look at this diagram. We know the height has to be an altitude or a perpendicular type of distance, so I could sketch that in anywhere. Generally, I like to sketch it from one of the vertices. So I'm going to do this. That right there represents the height. That's a vertical segment. So we know on a vertical segment, I should be looking at y values. Well, up here, I can see easily that the y value is 3, but when I look down here, I don't even have a point. Now, it shouldn't matter because I know all the y values down here are -1. So it doesn't matter what the x value of this point is. I know the y value is -1. So to calculate that, I can do top minus bottom. That comes out to be 4. So my height is 4. And my area will be 16. Okay, so for horizontal, we use x coordinates. For vertical, we use y coordinates. Number 6, find the area of the trapezoid with the following vertices. So once again, let's make ourselves kind of a rough sketch here. -2, -3, let's put that down here. A, -2, -3. B is -2, 5, so let's put that here. B, -2, 5. C is 6, 10, so up here somewhere. And D is 6, so same x distance, -3, same y distance. That would be D. So hopefully you see we have a horizontal segment here. right? These are both at 6, so we have a vertical segment here. These are both at -2 on the x, so I also have a vertical segment here. And then I'm going to connect this. So it's a trapezoid. It's sort of sitting sideways from the way we're used to looking at it. I know my area formula is 1/2 the height times the sum of the bases. So again, we're looking at it sideways. So my bases are going to be these two segments right here. Those are vertical segments. For vertical segments, I'm going to look at y coordinates. So I have 5 and -3, so this segment is going to be 5 minus -3, top minus bottom, that's 8. And this segment right here, my y coordinates are 10 and -3, so that's 10 minus -3, that's 13. So I have my two bases, 8 plus 13. The height on this one is pretty nice because this bottom segment here represents the height because it's perpendicular to both. That's a horizontal segment. On a horizontal segment, I'm looking at the x values and I'm taking right minus left. So 6 minus -2 turns out to be 8. And then I don't want to forget my 1/2. So finishing up, that's 1/2 times 8 times 21. Whoops, 21. Half of 8 is 4. 4 times 21 makes that area 84. That's the answer to number 6. Okay, let's quickly look at number 8 here. This one shouldn't have been too bad. We have triangle PQR with coordinates P right here at 0, 0. Q is at A0. So I'm out here at A, and I don't go up at all, and then R is at B10. So I can go out any distance R. I'm going to make this B, and then I'm going to go up 10, and I'm going to say this is point R. And so that is my triangle. And again, you could have put B actually anywhere on the x-axis, and this will work. It tells you the area is 100. So area of the triangle is 100. But I know area of a triangle is 1/2 base times height. So that should be 100. Well, I believe this segment represents my base, right? From 0, 0 to A0, that should be a distance of A. Remember B right here, just remember that represents this x coordinate on the axis. This is A0, so that distance is A. So 1/2 A. Now I need the height. Well, the height would come down here from R. That would be represented by the height. If I look to the side, wasn't this point up as high as 10? Which means that's my height. Equals 100. Well, half of 10. That's 5A is 100, and if I divide by 5, that means A is 20, and that's what they were looking for. So that's the answer to number 8. All right, on this page we're going to start with number 9. This is very similar to number 5. If you have your booklets open, you can look to the page on the left, except our parallelogram is going to be shifted kind of in a different orientation. So again, let's make kind of a rough sketch here. We have -5, 9. So let's do -5, 9 up here. And then I have 4, 5. So that would be maybe around here. Now notice we're at 4, -7. So I'm going to go out 4 again, but now I'm going to go down 7. And then I'm at -5, which is this same x direction, but I'm going to go down 3. So this is -5, -3. And again, just a rough sketch. We know it's supposed to look like a parallelogram, so hopefully we're close. And I want to find the area. So if you peek back at number 5, you'll see number 5, the orientation was more like this. We had a nice looking base, right? Because it was horizontal. But when I look at it this way, I don't really want to think of this segment as the base because it's not a horizontal segment and I can't find it. So again, I know my area formula is base times height. But I'm going to have to look sideways this time because my base is actually going to be this segment over here. I'm choosing that segment because I know I can calculate it because it's a vertical segment, and on a vertical segment I look at the y coordinates. The y coordinates are 9 and -3, so I do top minus bottom. That makes that segment 12. Now the height, we know the height has to be perpendicular to the base. So if it's easier, you can turn your paper sideways, right? So if you prefer to look at it this way and see that segment as the base, I'm going to go from one of the vertices and draw in a height. All right, so that's going to be my height. I know that has to be perpendicular, which means this is a horizontal segment. For a horizontal segment, we look at x coordinates. So I have a 4, but just like in the last problem, I don't know this point, but it doesn't matter because I do know that wherever that point is, the x coordinate has to be -5 because it's on that vertical line. So to get this horizontal segment, I would do right minus, and then the left x coordinate has to be -5, so that comes out to be 9. So my answer is 9 times 12, which comes out to be 108. Okay. Number 10 says find the coordinates of point B so that triangle ABD will have the same area as triangle ACD. So I need triangle ABD's area to equal the area of triangle ACD. And this is the area that we're making equal. Well, when I look at ABD, I don't know point B, so I'm not sure I can calculate that area yet. But when I look at triangle ACD, I know all 3 coordinates. So when I use my formula, 1/2 base times height, I think I can get that. I'm going to use this segment as the base. That's horizontal, so I'm looking at the 6 and the 14. Right? It's horizontal, so I do right minus left. So that appears to be 8 for the base. All right, I don't want to forget my 1/2 here. All right, the height. Well, this is an obtuse triangle. So I would go up to the opposite vertex, which is up here, and I would drop down a height. But since this is an obtuse triangle, the height actually lies outside the triangle. This represents the height. Well, that's pretty good news because I know this segment is up here at 9. So I know my height is 9. So 1/2 8 times 9, that's half of 72, which is 36. So now the question is, what do we do about triangle ABD? Well, I don't know this right here. That represents my base. So when I write 1/2 base, I'm just going to leave BD in there since I don't know it. But I'm looking at triangle ABD, and I can see that the height, this red segment, that was the height for triangle ACD, is also the height for triangle ABD. So I believe my height is the same, so I'm going to put 9 in there. So I have 1/2 BD times 9. So now I need to go ahead and solve that. So if I multiply both sides by 2, I get BD times 9 equals 72. And then if I divide, I'm going to get BD equal to 72 divided by 9, which is 8. All right, now they don't ask for BD. They want to know the coordinates of B. So what I have just found right now, if BD is 8, that means that this segment right here is 8. So how is that going to help me find the coordinates of B? Well, I know the y coordinate has to be 0. All right, think now. I need the x coordinate. I'm at D. D is at 6. If I'm at 6 and I back up 8, that would be 6 take away that 8. That would put me at -2. So again, if this distance BD comes out to be 8 and I'm at 6, I just take 6, back up 8, that's subtracting 8, puts me at -2. All right, problem number 12. A triangle has vertices at 0, 2. So again, I think we need a picture. 0, 2, Let's put that right on here. Let's mark that at 2. 4, 3. And 0y. Well, I know 0y means it has to be somewhere on the y-axis because the x-coordinate is 0, but I don't know whether I should put it up here or whether I should put it down here. And the catch is find both possible values of y. We're going to do both cases. All right, so let's first, in blue here, mark this point, and let's call this at y because that's the point 0y. And let's look at this blue triangle. Right? It says the area is 30. So if the area is 30, 30 should equal 1/2 base times height. So 30 equals 1/2. I'm going to look sideways. I'm going to describe this as the base. Well, the base, right, is a vertical segment, so it's top minus bottom. So this base could be described as y minus 2. The height of this triangle would be this segment right here. This would be the height. All right, if you look, that's a horizontal segment. Isn't that this distance of 4? So now if I solve that, I have 30 equals half of 4 is 2. If I divide by 2, I get 15 equals y minus 2, and then if I add 2, I get y to be 17. So that is one possible value of y. But now we said that we didn't necessarily have to put y above this 2. We could have also put y down here. All right, so if I call this the y value, and I connect to my original points, that red triangle represents my second possibility. So once again, I have 30 equal to 1/2 base times height. Well, this time, this piece is described by the base. I do top minus bottom, so that would be 2 minus y this time for the base. And my height, well, if this is the base, I go to the opposite vertex. This is an obtuse triangle, so the height is outside the triangle. It's from that opposite vertex perpendicular to the base. So you can see this green height is also the same for this red triangle. That green height is this distance of 4. So the height for the blue is the same as the height for the red. So now 30 equals half of 4 is 2. If I divide by 2, that's 15 equals 2 minus y. If I subtract, I get 13 equals negative y, so y would equal negative 13. There is my second answer. Number 13, this is a tough one. If the area of rectangle ABCE is 8 times that of triangle BCD, how far is D from the origin? So let's just write out this. The area of ABCE equals 8 times the area of triangle BCD. Let's see what we can do with that first and figure out how that's going to help us answer this question about how far D is from the origin. If I look at triangle, or rather rectangle ABCE, I'm pretty sure I can get that area, right? This point right here I can describe, right? In the x direction, that should be the same as the x direction at E, so that's negative 4, and I didn't go up on the y at all, so that's 0. This point right here is 16, 0. So if I'm looking to get the length of this segment right here, I'm going to look at x coordinate and x coordinate, and that would be 16 minus negative 4, which would be 20. So the base of that rectangle is 20. The height should be pretty easy to see. That's this segment right here. Isn't that just this y coordinate? I could look at the 5, and of course this is just 0, so that height is 5 minus 0, which is 5, and I can get that rectangle area to be 100. So now how does that help me? I need triangle BCD, which is this little triangle right here. So that's 8 times that area. So the area of a triangle is 1/2 base times height. Well, I'm going to look at this upside down, and I'm going to call this right here the base. I'm going to call that x. And I know this height right here should be the same as this height, so I know this height right here is 5. So I can say 100 equals 8, and then the area of that triangle is 1/2 a base of x and a height of 5. Now I just need to solve that. So I have 100 equals half of 8 is 4. 4 times 5 is 20. So that's 20x. So if I solve, I get x to be 5. That represents this distance right here. So now I know x is 5. So what does that tell me about point D? Well, think from here to here, this distance right here was 16, because this point was at 16, 0. So if I'm as far out as 16 and I back up 5, right? 16 come back 5 puts me at 11. And I know the y coordinate has to be the same as these y coordinates, which is 5. So again, since this distance is 5 and I know this distance is 16, I can go out 16, come back 5, puts me at an 11 as an x coordinate, and then the y coordinate is the same as these, which is just 5. But it doesn't ask for the coordinates of D. It asks this tougher question. It says, how far is D from the origin? So once I know D, I want to know that distance. Well, I just said it, distance. So can't I use distance formula? From 11,5 to 0, 0. So that's just 11 minus 0 quantity squared plus 5 minus 0 quantity squared. If I solve that, that's 121 plus 25. If I add that up, I get the square root of 146. That's how far D is from the origin. Okay, the tough part is getting the coordinates of D using this idea. All right, 14, similar but a little bit easier here. It says if the area of rectangle RCTN, so let's write this down, area of RCTN is 6 times the area of AECT, find the coordinates of point A. All right, let's start with this big rectangle, this RETN, this one right here. I think I can calculate its area. The coordinates of C, well, here's 0, 0. How far do I go to the left? Shouldn't it be the same as this point right here, which is 24, right? And we don't go up at all, so that coordinate is 0. So if I'm looking to get the area of that rectangle, I need this segment first. That's the base. That's horizontal, so I'm going to do right minus left. So I'm going to do 24 minus negative 12. That's going to be 36. Now I need the height of that rectangle. That would be this segment right here. That's vertical. That's top minus bottom. This is just at 0, so that's just 8 minus 0. And all of a sudden I have that left piece of the puzzle. I have 36 times 8. That's going to be 288. All right, now I'm looking at rectangle AECT. That's this piece right here. Well, I know that this piece right here is 8, but what I don't know is this distance right here. So let's call this x, like we did in the last problem. So that area would be 6 of those, and then the area of AECT would be 8 times x. So let's call that 48x. If you divide, you get x to be 6. So this distance right here is 6. Well, now we can do the same thing we did on the last problem, right? We need the coordinates of A. So now if you look below, we know the distance from here to here, right, was 24. So if I'm out here at 24 and I back up 6, that should be 24 minus 6. 24 minus 6 is 18. So my x coordinate is 18. My y coordinate would be the same as all of these y coordinates, and that was up here at 8. Again, we knew this distance was 24. We calculated this distance to be 6, so I go 24 and come back 6. That leaves my x coordinate to be 18, and my y value at A is the same as the other y values on the rectangle. All right, let's turn the page. We have just a few more, some of these three-dimensional ones to look at. So let's start with 20. Let's just see if you can get the sketch in here. It says draw the rectangular solid whose base has these vertices. So let's give ourselves a three-dimensional grid. Right, this is x, this is y, and this is z. So D is easy. That's at 0, 0, 0. A is on the x-axis at 4, 0, 0. So let's mark that at A. That's at 4. B is at 4, 5, 0. Now remember, this is the tough one to draw because you have to keep it in perspective. So I go 4 out on the x, but now I can't just count 5 over on the y, because if I do that, I end up putting my point out here. You have to keep it in perspective. You go 4 on the x, and from here you count over 5. 1, 2, 3, 4, 5, 0. So that's B. This is 5. And then C is 0, 5, 0. That's the point on the y-axis. That's C. If your bottom doesn't sort of look like a parallelogram, then you've probably done something wrong, because that is a rectangle sort of given the perspective we're looking at it. Now we have a height of 7. So what I would do would just be to take maybe another color and from each point draw the same length segment best you can and call that 7. And then connect. So those green heights are all 7. All right, and that's all you had to do for number 20. Draw the rectangular solid with that base whose height is 7. 21 actually asks you to answer those questions. It says find the area of the base. So hopefully you can see this length is 4, right? And this length is 5, right? That's a rectangle, so 4 times 5 is 20. Remember, it just looks like a parallelogram because of the angle we're looking at it. Find the volume of the solid. Well, it's a rectangular prism, so volume is area of the base times the height of the solid. So in our case, we already know the area of the base is 20, and the height of the solid are those green segments, which is 7, so that's 140. The last one asks for the diagonals of the solid. We've done that before. Remember, that's the one that cuts from a lower vertex across through the middle of the cube to an upper vertex. That's a diagonal of the cube. It cuts right through the middle. I like to always pick 0, 0, 0 as one of my points. And then my other point here would be 4, 5, 7. And now I'm just going to use distance formula. So 4 minus 0 squared plus 5 minus 0 squared plus 7 minus 0 squared. If you work that all out, that comes out to be the square root of 90, but of course we can simplify that to 3 square roots of 10. Okay? All right. I realize I skipped 15 and 16 at the top, so I'm going to go back up. I'm sorry I'm doing these out of order. 15, the endpoints of one diagonal of a rhombus are these two, and that's a diagonal. Let's keep that in mind. And then it tells us the area of a rhombus is 150. So immediately I start thinking about a rhombus, and if you remember from our area chapter, we can think of a rhombus either as a parallelogram or we can think of a rhombus as a kite. I particularly like thinking of it as a kite because if you remember the formula for a kite, the area is 1/2 diagonal 1 times diagonal 2. And that really seems to have a connection here since they're giving us one of the diagonals. So if I know the area and I can calculate one of the lengths of the diagonals, I should be able to find the other diagonal. That'll be helpful in getting us to the perimeter. So I'm going to start with that. I'm going to say diagonal number 1, I'm going to use distance formula on. That would be x minus x quantity squared plus y minus y quantity squared. That would be the square root of 12 squared plus 19 minus 2 is 17 squared. Or I'm sorry, 19 minus, this should have been 3. This is the 3 right here, so that should be 16 squared. And if you calculate that, it comes out nicely to 20. So I have the area is 150. 1/2, one of the diagonals is 20, so now I should be able to find the length of the other diagonal. So 150 equals half of 20 is 10. If I divide, diagonal 2 comes out to be 15. All right, now we need perimeters. So sketch yourself a rhombus and think about what you know. Right? I know one diagonal is 20. That seems to be the longer diagonal, and the other diagonal is 15. I know diagonals are perpendicular, and I know they bisect each other. So this diagonal of 20 is 10 and 10, and this diagonal of 15 is 7.5 and 7.5. So now if I need perimeter, I need this segment right here, or we could find actually any side. Hopefully you realize now we have a right triangle. So I can say x squared equals 10 squared plus 7.5 squared. If you do that, you get x to equal the square root of 156.25. And if you do that on your calculator, you happen to get 12.5. Okay, remember we're not done yet because it asked for perimeter. So perimeter, there are 4 sides, so I would take 4 times 12.5, and that actually comes out to be 50. That is your answer. Okay, so the trick is to use the area formula for a rhombus. Knowing you can calculate one diagonal, it gives you the second diagonal, which then allows you to create a picture with these right triangles. All right, and 16. This is also similar to one we did before. Find the area of a triangle with these vertices. So again, let's make a quick sketch. We're at -2, 3. We're at -2, -5. And we're at 6, 1. I think once again this is similar to the parallelogram one we had. The only difference is we're kind of looking at it from a sideways perspective. We know area is 1/2 base times height. The trick, of course, is we have to look at this sideways, so we should be looking this segment as the base. That's vertical. That's 3 and -5. So 3 minus -5 is 8. That's my base. 1/2. I need the height. Well, the height would be from the opposite vertex perpendicular to that, but if it's perpendicular to vertical, it means it's a horizontal segment. Horizontal, I look at x. 6, again, I don't know this point, but I know all the x coordinates have to be -2, so that segment would be 6 right side minus left side, -2. That comes out to be 8. So half of 8 times 8, that's half of 64 is 32. All right, now we'll go on to the next page. Sorry about the order. One more, and this is pretty straightforward. I just wanted to give you an example of one of these. Find the point that is 1/4 of the way from 9, -4 to 21, -16. So I'm starting at 9, -4. And I'm moving along to 21, 16, and I'm moving 1/4 of the way, and I'm looking for this xy. All right, so if you remember, to get the x coordinate, you take the starting x coordinate, which in our case is the 9, because this is my starting point, and I'm going to add on 1/4 of the x distance. To get the x distance, I look at the x values. which are 21 and 9. And to get that x distance, I take 21 minus 9. So that's going to be 9 plus 1/4 of 12. That's 9 plus 1/4 of 12 is 3. So my x coordinate is 12. Similarly, to find the y value, I take the starting y coordinate, which is -4. This is the point I'm leaving from. And then I'm going to add 1/4 of the y distance. The y distance is represented by the y coordinates. That's right minus left. So I'm going to do 16 minus -4. So that's -4 plus 1/4 of 20. -4, 1/4 of 20 is 5, so that comes out to be 1. So my point is 12, 1.